Lecture 3.4, boiling, bubbling, and evaporation. So the first thing that I want to do here is that I want to talk about boiling, these so-called bubbles, and atmospheric pressure. Suppose we have a container of water that's under atmospheric pressure. So a container of water under atmospheric pressure has water molecules that are moving fast enough to break intermolecular bonds. And what happens in this process is that you get a phase transition from water to water vapor, a liquid gas. This happens because of the Maxwell Boltzmann distribution. So what you're seeing here is that just above the water level, there's a water vapor layer. So just above the water level, there is a water vapor layer called the vapor pressure region. And what this is here is that this tells us here is that this is a location no, let's not say that. The escaping vapor molecules are kept in place there by atmospheric pressure. So if I was to draw my container, I'm seeing something like this. So I have a container. This is sort of like a beaker. And now I have a water level right here. And what I'm seeing with this water level is that right above it, I have this layer of water vapor. And so in this layer, what I'm seeing here is that I'm seeing the escaped water vapor molecules. And then right above here is atmospheric pressure. So what I'm seeing here is that you can clearly see that this right here is the water level. This right here is the vapor pressure region. And up here is atmospheric pressure. And the reason why there's a water vapor barrier there is because atmospheric pressure is keeping it in check. So what keeps the vapor pressure in place is that the atmospheric pressure is not allowing those water vapor molecules to escape. So then let's move on here. So then the word boiling enters the picture. Now, if the vapor pressure reaches slash exceeds atmospheric pressure, due to heating, then water boils. In other words, if the vapor pressure, or if the atmospheric pressure is greater than the vapor pressure, then we find that it is, you cannot, there's no boiling that occurs. Oops, that's wrong. So what you're finding here is that there's no bubble formation. However, if the pressure of the vapor barrier is greater than P atmosphere, then we have boiling. So here, that tells us here is that bubbles are formed at 100 degrees C while at 1 atmosphere. So here we go. We can see here, we see here that boiling of water depends on pressure. So let's look at what do I mean by that. So the first thing that we should talk about is we can have higher pressures and be achieved in pressure cookers. Okay, so let's look at this guy. So what happens in a pressure cooker? So a pressure cooker is an isochoric process where increasing pressure causes an increase in temperature. According to the isochoric condition. In other words, the ratio of temperature to pressure has to be constant. So if I have a higher pressure, then I must have a higher temperature. And that has to be a constant. So what I'm seeing here is that I'm seeing this here. This guy right here, this is the pressure increase of cooker. As a consequence, in order to keep that constant, the temperature exceeds beyond 100 degrees C. And as a consequence, because the temperature is higher than 100 degrees C, foods cook faster. So let's look at this a little bit more carefully now. So from a molecular viewpoint, water molecules bond via electrical interactions. Because water is polar, that means it has a positive and a negative in. The oxygen atom is negatively charged, while hydrogens are positively charged. When liquid bonds form, it looks something like this. So I could imagine that I have a hydrogen atom, an oxygen atom. Okay, so here's my oxygen. Now, what I'm going to see here is that now I have attached two hydrogens here. So that means here's my oxygen, here's my hydrogen. And so now these guys are polar. So what does that mean? That means that the oxygen is negative and then the hydrogens are positive. So now what we can do here is that we can form a bond. So the way the bond is that the oxygen is now attracted to the hydrogens. So again, here's my oxygen, hydrogen. If I look at my signs, you could see that this is negative, and then these guys are positive. And so what I'm saying is that this is the bond that breaks during phase transitions. Of course, I mean, I can also have other connections to these, right? I could have an oxygen attracted to that proton or that hydrogen, which is the same actually. So if I look at this here, I'll stop after this, but you're seeing that how they attach to each other really depends on the polarity. So then this is negative, and then of course these guys are positive. So now, again, I could now start the chain. I could have bonds that go something like this. I could have bonds that come like that. So I start the whole process all over again. And then this guy here is going to be the negative. This guy is going to be the negative, which the opposites attract. And so again, I have my hydrogens right here. And these guys then will then bind something like this here. So what happens here? In a pressure cooker, the added pressure makes it harder to break these electrical bonds. And therefore, more heat transfer has to occur This in turn increases the temperature above 100 degrees C. That's why pressure cookers can cook at a higher temperature, but it has to do with the pressure. Now, the other thing that we can do is that we can lower pressures can be achieved at high altitudes. So if you look at this thing, the Mile High city of Denver has a lower atmospheric pressure. So if you were to compare the pressure, so the atmospheric pressure in Denver is equal to 83% of the atmospheric pressure at sea level. That means it's 17% less pressure on, let's say, a glass of water. This decrease, decrease in pressure decreases the boiling point of water to around 95 degrees C. So right away, you're going like, wow, it decreases the boiling point, so therefore it should be easier to cook food. That's not true. So if you're cooking pasta at a higher elevation, it actually takes longer because water boils at a lower temperature at higher elevations. Foods that are prepared by boiling, while they boil at a lower temperature, and therefore it's going to take longer to cook. So this question of low pressure boiling now comes into play here. So the example of Denver is a good gateway to talk about the language of boiling. And that language, in my opinion, is murky. I mean, this is analogous to the language of heating, right? So when you say turn on the heat because it's cold, is not thermodynamically correct, right? Instead of being PC, you need to be TC, thermodynamically correct with the language. And so we need to separate the concepts of boiling, which in like I have to tell you this requires heat transfer versus bubbling. And here there is no heat transfer to be thermodynamically correct, to be TC. So the question is, maybe we should start this as a question. What does it mean to boil water? So let's think about how we look at this thing. So everyday language implies that boiling water requires heat transfer. Heat transfer to the water. So if you boil water to cook pasta, but let's be careful. What do we mean that we're going to cook pasta? I would say that two things happen when one cooks dry pasta. One, it hydrates the pasta by absorbing water. That's one. And then two, the proteins in the pasta flour must be broken down. That's what we mean by cooking pasta. So if we boil water to cook pasta, one has to increase the temperature, in other words, heat transfer, to break, how do I say this? Yeah, break down the proteins in the pasta. Now, I've heard people say just the contrary. They say, well, if one soaks pasta in water, it rehydrates. It rehydrates it. But this is not cooking, since heat transfer is required to break proteins down. It's not cooking. Okay. So now, again, we're still with the language of boiling. Okay. So to start to understand what boiling is, we start with the Maxwell Boltzmann curve. And so if I insert an image, here's this image here. So what we want to focus on is we want to focus on the activation region. Okay. So here we want to focus on this region. So what happens with the activation? Water molecules with activation energies or kinetic energies have enough energy to break liquid bonds. Now, what I'm saying here is, which I probably should have said this, I'm going to assume that this is just room temperature spread at 20 degrees C. So there's no heat being added here. And form water vapor. So in other words, at room temperature, there is literally a phase transition in a glass of water, which is crazy. And so these microscopic bubbles are formed due to these phase transitions here. So let me be careful here now. So these are what I call bubbles. They're not due to heating. These are due to the activation energies that cause phase transitions. Remember, no heating. So there are two competing pressures. So for starters here, let me bring this up. I imagine that I have a bubble. Okay, so I have a region of phase transition, and I'm going to say that this right here is where the bubble is right there. And then all around in this room temperature glass, I have water here. So now the two competing forces here is that in here, I'm going to say that inside of here is the pressure of the bubble, which is pushing out. And then I have the pressure of the atmosphere. And this is the pressure of the atmosphere. So I'm actually going to copy this and then modify it as we go along, because this is a good picture to have. So Here we go. So now we're going to look at two regions. So we're going to focus on two regions. One is at the surface of the water and the bottom of the glass or the water glass. Okay, so here we go. So now we're going to focus on the surface. So if I look at the surface, what we're seeing here is that bubbles formed at the surface only compete with P atmosphere. So for activation energies, bubbles are formed, and that's because the pressure of the bubble is greater than the pressure of the atmosphere and escape into the vapor pressure region. So again, how do I draw this picture here? So what I'm seeing here is that I have my container again. So here's my container. By the way, let me put this over here since I just copied this. Okay, and I'm going to modify this guy here in a moment. So what you're seeing here is that if I have my container, let's say that here's my beaker, and right here is the water level. And what's happening here is that now I have a little bubble right here, right at the surface. Well, that doesn't really work. It has to be below the water surface. So then I'm looking at this. So then here's a bubble right here at the surface. So if I look at this water bubble at the surface, what you're going to see here is that this rises and then it releases the water vapor. And then, of course, I then have atmospheric pressure right here. So the reason why I have these bubbles here is that I'm seeing these guys escaping, and I'm going to have these water vapor molecules into that thing. So here, the pressure, we can then say that the pressure of the bubble is greater than P atmosphere. So picture-wise, the reason why they escape here is that I gotta go in and I have to make that pressure larger. So this pressure is larger for the bubble, and therefore they burst and they release that water vapor. Now, what happens if we're at the bottom of the glass? So one does not see bubbles at the bottom. And the reason why is because there's two pressures. So what I'm going to do here is that I'm going to copy this, and then I'm going to modify this. So if I look at this thing, here's what you're seeing. So here's my container. And so what I'm going to do here is that I'm going to do this. I'm going to move this over here. Now what happens here is that I have two pressures. Okay, I have two pressures. So if I come here and I just modify this just a little bit, here's what you're going to see here. Again, I reestablish my water level, and then of course I have my vapor barrier. But now I'm going to put my bubble down here at the bottom. So the fact that I don't see bubble, that tells me that I have two competing pressures once again. One, I have the pressure acting down, that's the pressure of the atmosphere, and now I have the weight of the water. So if I look at the pressure at the bottom, it's a combination of the atmospheric pressure plus the weight of the water, and the fact that no bubbles are formed, the pressure of the bubble must be less. So then I'm going to modify this picture again, and let's see what happens here. So what I'm seeing here is that if I look at the pressure of the bubble, it's now less. But the pressure of the atmosphere is now larger. And because it's larger, we are then seeing here that no substantial, it's not, how do you spell substantial? Substantial size bubbles will form, because the pressure of the bottom of the glass, which is intimately connected to atmospheric pressure, is strong enough to squish these out of existence. Oops, that's an A. Once again, no bubble formation. So now there are two ways to make P vapor, which I call P bubble, larger than P atmosphere. So one, you have to add energy and increase the overall KRMS of the water molecules. This is what I call boiling. The other way is that you can reduce P atmosphere, which then allows bubble formation, not due to the increase in temperature, but it allows bubble formation because of the activation energy. So let's talk about those two processes here. So the first process, we're going to say that we have boiling via heat transfer. So how do we cause a boiling, right? The boiling process, like I have to tell you how to boil water, is the constant heat transfer between stove, pot, and water. The metal pot increases KRMS of water molecules that cause pressure of the bubble to be greater than the pressure at the bottom of pot. This is the cause of bubble formation that rise to the surface and release water vapor, which we call steam. At 1 atmosphere, that happens at 1 degree Celsius. So in this case, what am I actually seeing here? I'm seeing something like this. I have a container, and let's say this is my pot. And then what I do, of course, is that I come in and I have a heat source. And this heat source is constantly right? It's constantly doing what? It's forming bubbles. So I have a lot of bubbles that are forming and moving up. So what happens here is that now I have a lot of water vapor in the pressure. So in this case, you're seeing that these guys are just, there's a lot more vapor pressure. And this is what we call boiling. And that's because the vapor pressure has exceeded the you know the atmospheric pressure. Now we have the other situation. Low pressure bubbling with no heat transfer. And here's where I say there's a problem. We have a language problem. That's not TC. It's common to call this low pressure boiling. In fact, you'd have to look, when you look it up, that's exactly what they're talking about. So this is due not to heat transfer, but to the activation energy of the Maxwell-Boltzmann distribution. Furthermore, we will see that the temperature actually decreases in this process. So again, it's a different process. It's not a heat transfer. It's due to the activation here. So the way it's done here is it goes something like this here. So what we do here is that to reduce pressure, one uses a airtight container with a vacuum pump. And so what happens here is that I have an image that looks something like this here. And so what you're seeing here is that if you look at this container, this right here is the glass container that's airtight. There's my glass container. And the reason why you wanted a glass is because you want to be able to see it. And then if you look at the hose right here, this leads to a vacuum pump. And the whole goal of the vacuum pump is it pulls air out of the water. And then right here, you'll see here is that this is our water glass. In this case, it's a beaker. So what actually happens here? So the vacuum pump pulls out the air that reduces pressure to allow bubble formation. So let's be really clear about this. So I'm going to talk about an analogy now. So the analogy I want to talk about is that I want to talk about adiabatic cooling. In adiabatic cooling, by spraying a can of, let's say, hairspray, the fastest particles escape. Leaving the slowest ones. So therefore, there's a temperature decrease. This is exactly happens in this vacuum pump slash glass container. When you remove air, the fastest air water vapor are removed cooling down the water, not increasing the temperature, right? This is very different. So what happens here is that this implies bubbling occurs at low temperatures, not high ones. In fact, if one continues to do this, one can freeze, the water. So there are 3 links here. So if you look, there's video links. There's 1, 2, and 3. These 2 are short, and we should look at them. This one is longer, but it's the best one. Because this one, they'll show you how bubbling water freezes it. And that's worth looking at. So I'm not going to do 3 here. So what I'm going to do here is that I'm going to go and I'm going to share my screen. Well, I'm not set up here. Give me a moment. Okay, I have the links now. So this is the first link. This is link number 1. So check this out.
You can see I have some water. It is only about 45 degrees. I'm going to put it into this vacuum pump.
So note that that water is warm. It's above room temperature. It turns out that if you warm the water, you can remove immediately the fast-moving particles. Now check this out.
Suck the air out from above the warm water.
Look at the bubble formation.
Whoa, my water's boiling at only 45 degrees or less.
Okay, remember what he said. It's boiling at 45 degrees or less. Again, I would say that that's not TC. Now let's look at this other video here. It's very similar, but you can actually do this at home. That's the reason why I'm showing you. Again, you see the hot water to make it bubble faster. You can see the bubble formation. So that's what we mean by this. Okay. So again, make sure you look at 3 here. So let's do the last piece of this. And this is, it's going to be a short one. This is evaporation of water at room temperature. We've discussed several times now the word evaporation but never explained it. Let's make it official now. So suppose one spills some tea into a tea saucer. You know, this happens to me, maybe because I'm clumsy here, but I could imagine that if I have a cup, and then what I'm going to do here is that I imagine that here's my tea, and then right here, I'm going to have my handle, of course. So in here, I have my hot tea, and let's say that I'm drinking out of a green cup. And then my saucer here is going to be in yellow. So what I'm going to do here is that after I finish drinking my tea, I'll see that there is water in the saucer. So if I look at my saucer now, you'll see that I have a little bit of water right in the saucer here. So what happens here, what you want to do here is that water eventually will evaporate, right? So here I go. So the question is this: how does water evaporate at room temperature? And you may already know, right? It has to do with what? It's about the Maxwell-Boltzmann curve. And the activation part of the curve. So again, if I'm looking at this guy here, here's my curve again. And the only point I care about is right here. And let's say here is that this is at 20 degrees Celsius room temperature. So then what happens here? I'm going to go through my process here. So water vapor escapes from the surface because its activation energy causes phase transitions. Two, since the highest KRMS molecules escape only the lower KRMS molecules are left, and the water in the saucer cools. So what happens next? The air is now warmer than the water in the saucer, and heat transfer occurs and reestablishes the Maxwell Boltzmann curve for 20 degrees C. So what happens? The process continues until there are no more water molecules left.